All right, so for today we're going to see how far we can get into the last bit of analytical geometry, or analytic geometry. Okay, so the main idea we're going to be chatting about today is just changes of dimensionality and orthogonal projections. So very many powerful and useful machine learning approaches involve dimensionality changes. In the case of support vector machines, you work in a dimensionality typically higher than the original data. So the idea there is that data is not always separable, but if you blow it up into an extremely high dimensional space, those little minor variations in the values in those dimensions will then allow you to separate out into higher dimensions. So this has become recently very topical for like transformer models and things like that, because the Claude LLM by Anthropic, what they've started to find is that the embedding space of tokens in these models tend to be highly overlapping, and so you end up with something like, like that'll be a part of your token, and that'll be an embedding, and that'll be an embedding. There's this like really small difference between the two of those vectors, right? And so if you're just trying to interpret what the activity or what's going on with these embedding spaces, in those cases, you're going to say that those are confusing concepts. But what they're starting to find is that that's how the neural network naturally embeds very distinct concepts. So, the one on the right will be dog, and the other one will be, a construction vehicle or something. And so this is called superposition in the neural network embeddings. And it's kind of extremely amazing that this has happened. The problem with this is that in the one case where in the world where your LLM has to deal with a dog and construction at the same time, you're now in trouble. Okay, and you're going to start getting confused. Your model's going to start producing hallucinations. But the idea is that you can actually share these representations in space as long as you're never really queuing the same token at the same time. What they then did is they then went and blew up this embedding space into an extremely high dimensional space using what's called a sparse autoencoder, and that sparse autoencoder detects the little minor variations in the vectors there and gives each vector its own dimension essentially. And then now you have distinct concepts, and now there's no ability to be confused. And what they found is that there was a dimension exclusively to the Golden Gate Bridge, and that's where that Golden Gate Claude concept came from. They also claimed very loudly at a conference last year that they had found a dimension in the sparse space that corresponded to the LLM recognizing that it could be evil. And then they were like, but don't worry guys, we switched it off, and then claimed that that was them enforcing safety in their models. So there's a lot of very topical ideas in this idea of blowing up into extremely high dimensional spaces that are being employed now in machine learning. On the other side, there's the more classical approaches, which are a lot of visualization techniques, require us to reduce dimensionality. So you're going to be projecting down into like a 2D or 3D space. A lot of times as well, if you kind of are changing your representations of space, that can be really useful. So for example, I like this representation at the top here, where let's say this is our data set and we're trying to separate dots. We're trying to separate dots from squares. Then if I'm using a linear regression to do this, it's not going to work, right? But it turns out if I'm trying to use the radius and the angle and I switch to polar coordinates as my representation of space here, now it becomes extremely separable just based on the radius. Okay, if my data point is in a radius larger than this boundary, it's now an X and dots otherwise. Okay, so now it's very easy, and a logistic regression can then solve it. So the way you represent your features matters, and so this kind of idea is going to, this is where this idea is starting to come out in. Okay, so ideally you want to want this mapping to preserve as much information as possible. And so for example, principal component analysis does this using eigen decomposition, which will go in, or singular value decomposition, depending on how you do it. But it's something we're going to go into in the next couple of weeks. But today we're just going to be going into orthogonal projection, and orthogonal projection says that what we're trying to do is take all of these data points in blue here and find their closest point along the line. All right, and I drew the line over just in that purple vector. So what we're just going to say is, well, if I want to get those blue dots onto the line, the quickest possible way for me to do that is to just obviously go straight down. All right, there's no benefit towards taking a kind of non-direct path onto the line. You're just going to go straight towards the line. It turns out that if you go straight towards the line, what that corresponds to is taking the path perpendicular to the basis vector in black or in purple there. Okay, so purple would be your basis vector, black line would be the lambda times that one basis vector. Okay, So let's say a projection from R2, as you can see, we have X1 and X2. You're now projecting down onto the line, which will then be a real number, right? So if you want to lie over there, on the red vector, that's then equal to, so red vector is equal to, what's it, -2 times the purple. Okay, for argument's sake there. All right, so you have your basis vector, and now you're going to represent any points along that line with it. And we just want to find this coefficient for every single dot. We just want to find this coefficient for every single dot. Where does it lie along my basis vector such that it's now represented only as a linear combination of the basis for the purple line? Okay. So the first thing we need to understand if we're going to make some progress on that problem is the notion of a projection. A projection is something that's really actually simple to understand. The whole idea is that if I apply a mapping, any sort of mapping onto this line or mapping between sets, if I apply it once, it's the same as applying it twice, and as an extension, it's the same as applying it n times after. All right. So once I've applied a mapping once, if applying it again does nothing, it's then a projection. All right. And so you can see why this is coming up here, because if I project this dot onto the line, it's now sitting there. If I try to project that dot back onto the line, it's just going to stay there. Okay, which is why it's called orthogonal projection. Okay, orthogonal because we're going straight to the line, projection because I only have to do it once and then it's done forever. Okay, so let V be a vector space and U is some subspace of V, then any linear mapping pi is called a projection if again twice. Usually denotes it as pi squared, but you know this as being the composition of the mapping or the operator. It's the same as doing it once. Since linear mappings can be expressed by transformation matrices, we also have that if P is a matrix applying that mapping, so this mapping pi is being represented by the matrix, then multiplying that matrix out twice is the same as multiplying it once. Okay. And so we can start by looking at the projection onto the one-dimensional subspace. This is the easiest possible example of this. So we get sitting in a 2D space, want to embed into a 1D space along that yellow basis vector. Okay, so we want to project X onto a line, so one-dimensional subspace, through the origin and defined by the basis vector B, where we're spanning B, and U is the subset of Rn that's spanned by B. Okay, this is a general case, but again, for the moment, we're just looking at B being one-dimensional, being a single line. Specifically, when we project X onto U, we wish to obtain the pi of U that is closest to X. Okay, so again, we're projecting by the pi onto the subspace U defined by our basis vector B, okay, and it's operating on X. So that's how we read that. It's a little bit notation-y, but that's the whole point. And so this is going to keep coming up. It's worth, at least for the next half an hour, having that notation in mind. That is this point along my basis vector that I'm projecting onto for X. Okay? And as you can see, once again, it's 90 degrees, so orthogonal projection. Okay, so it is worth being precise in our requirements of this mapping. So the projection pi U of X is closest to X when the distance between the two is minimal, right? So this is saying, obviously, this is our norm, so you can be using the L2 norm in this case. All right, there is the general case, and we will discuss that in a little bit. But for now, just think of it as being Euclidean, the Euclidean norm of the dot product as our inner product. So we're now saying the distance covered between our projection and the original matrix must be minimal. So what we really want to do is cover this bit here. This is that norm X minus pi U of X. All right, the red dashed line. That's what we want to minimize. Okay, and so this occurs when that difference is orthogonal to U. So again, it occurs when red vector orthogonal to the basis vector. It does depend on the inner product you're using. Again, it's we're going to be general in a second. So it doesn't always have to be that straight line. That's what it looks like when you're using Euclidean metric. All right, we covered the idea of having different metrics and different bases. But for the moment, it's easy if you just imagine as being 90 degrees. But what it really is 90 degrees in terms of your inner product. Okay, and that doesn't have to be the Euclidean or the dot product. Okay, So since the mapping pi maps x onto u, there exists a lambda such that after I've conducted the mapping, I can now just write my new data points, my projected data point, as a linear combination of this basis vector that I just projected onto, right? My new point here lies somewhere along my basis vector, and as a result, I can write it as a, quote, linear combination of my basis vector. There's no combination because we're only in one space. We only have one basis vector, but still, that's the whole idea for now. Okay, and so the idea of the way we build out this projection matrix is we follow the 3 following steps, and you can kind of just, you know, run them forward. Again, I like the idea that when you're doing mathematics, you know when to rely on intuition, when to rely on geometry, when to rely on algebra. This is a case where I try to sometimes keep the intuition of this almost entirely distinct from the algebra, because the algebra is just following this process. It is a very clean step-by-step process that you can do. Okay, the red scribbles here is stuff I've done in previous years just to make the steps easier. It's not like an intermediate thing or anything too big. If you can understand just these steps, then by all means follow that. But I just wanted to make things clear. Okay, so the first thing that we're going to do is we're going to determine the coordinate lambda, all right? So what is the coefficient of that data point there in terms of my basis after I've done the projection, all right? Given the test today, I hope that's somewhat clear. Okay, so what this means is ultimately that we want the orthogonality condition to be met. That's the start of this process. I know that in terms of my inner product, the quickest way to get onto the basis is to move directly towards it and be orthogonal. All right, so inner product must have that red dotted vector. All right, the difference between x before and after the projection must now be orthogonal, have an inner product of 0 when it's computed with the basis vector. Okay, that's the start. Now I'm going to go and substitute in my representation of the data point after the projection into the second step here. Okay, so we know that after the projection, I'm writing my new data point as a linear combination of my basis. That's what this lambda b is. Okay, then we know that we can apply the linearity, or there's a bilinearity of our inner product. And so we can just FOIL those things out. And so we end up with x times b, and then the lambda FOILs out to be b times b, and then you pull out the scalar. All right? And so we end up saying, what is the inner product of xb minus lambda times the inner product of b with itself? You now rearrange your terms. And again, this is, you know, fairly standard, at least in 1D. We're just going to take lambda inner product of b with itself over the line and divide by b inner product b. And so you end up with this term here. Again, we know that in this case it's a basis vector, so it's not going to be the 0 vector, so there's no chance of you dividing by b here. So you can be happy that we're not going to now, dividing by 0 here. You can be happy that this is a well-defined operation that you're doing if you have a basis vector that isn't obviously 0. Okay? And then lastly, we're now just going to say you can reverse, so this is the same as then the norm of b. And then because of this property up at the top here, you can just reverse the ordering of bx over there. Okay? This will now give you a representation of your coordinate for lambda. All right? So if you use your current context and choose the inner product to be the dot product, then you know that then just, you know, this x for the dot product is now b transposed x. Okay, so we're substituting that in the top there. If your basis vector is unit norm, then this gets really easy because all you're doing now is just multiplying your basis by x. Okay. So that's the first step. That's all you ever have to do. Solve for the coordinate. We now know what the coordinate is for our data point after the projection. Okay. This is now going to take a slight detour just to chat through things about like the cosine and that and stuff. So finding the projection of the point after that, we now know that this is equal to lambda b. Okay, and so it follows that all we're going to do is substitute in what we just calculated for lambda into this equation up here. Okay, so that's the exact form there. And then once we kind of reversed it and then also said the inner product was the dot product, that's what we got there. So you might be asking, well, what can we say about the norm of the vector after the projection? Okay, and so we know then that in this case, especially if you're normalizing your basis vector, it's just there. We have this identity here where we can FOIL out any constant from a norm, and you get the absolute value of lambda. That was something we spoke about last week. I'm not going to harp on that for the moment. But if the dot product is used, then we can tie in our earlier angle definition. Okay, and so we have this representation over here. We're taking the norm now of our projection after x. Okay, and we know from last week that we have this formula for our angle cos of theta, right? So if we rework this representation for cos of theta, you can take the norm of b over and the norm of x over, and so you end up with this representation that says the b transpose times by x absolute valued results in all of those terms there. And we're just going to substitute that in. Okay, we're just going to say this bit was found there. I'm going to replace it with that. Okay. And then lastly, you cancel your terms. You have b norm, b norm, b norm squared. Those all cancel. And so now all this is saying is that the norm of my vector after I've projected onto my basis is just the norm of the original x scaled by cos of the angle of those two vectors. Okay? If we were projecting onto a basis, and let's get back here, instead of working with that line, that was a bit skewed, but instead of working with that black line, we were working there. Okay? At that point, we're in 90 degrees, so cos of 90 is going to give us 0, and our orthogonal projection is going to give us lambda equals 0. Okay? Similarly, if we're already working on that, we have 0, there's no angle, and so then cos of 0 gives us 1, and so the norm of pi of x will just stay the same, and it's just the norm of x. Okay? So that's just a nice result that proves that what we're doing is correct. We're at the very least getting to intuitive results that say that, well, my new norm is equal to my old norm updated by just the angle between the two. Okay. But returning to the original point of this whole exercise, we're now going to try and build the projection matrix pi, or P of pi. All right, so we want to actually get the matrix that allows us to project onto the line, not just the coordinate vector itself. Okay, so firstly, since the projection is a linear mapping, and our domain and codomain of finite dimensional vector spaces, there has to exist a matrix P such that we can map onto it. This is very similar to us just saying earlier that this norm was guaranteed to not be 0. Okay, we know we're projecting onto something that's not the 0 vector. We know that x itself wasn't the 0 vector, but even if it is, you'll just get back to 0 in this case. So we know that what we're doing is going to be well defined. You're not going to divide by a 0 anyway and get something that's wrong. Okay, so once again, we remind ourselves, pi of x after I project onto the basis, my new point is a linear combination of my basis vectors. You can then, there's commutativity with respect to a scalar product of a vector. And so we can then put the lambda on the other side and substitute in its values. At the end of these slides is a slightly reformulated way of this process that I prefer. So one thing I don't like about this process is the way it's in the textbook and in these notes, is that it goes B transposed. And what that corresponds to is you're taking a vector, a vector multiplying by what's called a covector, or just, a row vector. And so you end up with a 2 by 2. Right? There's a way of actually just doing this operation where you multiply b and x first, and you end up doing scalar multiplication rather than matrix multiplication. I have no idea why they went with this way in the slides, but I do show you an example of you doing the other way in a note at the end of this. I don't think we'll get to it today, but I do show you another way of doing it, which I find much safer and easier to do in tests and things like that. Okay? Either way, we know that matrix multiplication is also now associative. So I don't have to do it that way first. I can also group it in, go with those b terms first as well. Okay? And this b squared, because it's a norm, that's a scalar. So don't forget that that's now a scalar value, so it can just move around pretty freely. All right. So in this thing at the bottom says, recall that b is an n by 1 matrix and b transpose is a 1 by n matrix. Therefore, b transpose is an n by n matrix. And so the projection is that. Okay. In other words, what is the matrix such that when I go multiply x by that matrix, it gives me my new updated dot or my new updated data point. It is this matrix on the right-hand side of x. So that is, maybe that's why this slides did this. It's because they want to get a matrix out of it. Okay. And so that's the actual projection matrix. So in a test, let's say, I might ask you for the coordinates along the basis line that you're projecting onto, so lambda. I might ask you for the matrix itself, so B transpose times by B norm squared. Or I might then ask you for the last bit of this, which is, I might also ask you for the second bit, actually, which is the projection after that. So lambda times B. Okay. So in that case, you will give me this full term there, or rather this full term here. Okay, any of those three things can come up. Okay, so just one important projection remark. The projection we have been working with produces a vector in Rn. However, we no longer require n coordinates to represent the projection, but only a single one if we want to express it with respect to the basis B that spans the subspace U, which is just lambda. So in other words, we started off embedded in this case in R2, right? We had data in R2, but the basis vector itself that we're projecting onto is also sitting in R2. It's embedded in that space, right? We spoke about the embedding dimension. It's embedded in R2, but we've now projected our data points onto it, and it's only a one-dimensional line. We're going to generalize to more dimensions now. But in that case, if I want to remember just the projected value of all of my data, I just need these new lambda values that represent how far along the basis I am lying. Okay, so that is a form of projection. In this case, we went from needing to remember, what, 1, 2, 3, 4, 5, 6 two-dimensional data points. Now all we need to do is remember one two-dimensional data point, in other words, the red line. We need to remember how it's embedded in the space, and then how far along the line all of my data points exist. Okay, so I've lost about 6 values I need to represent at the cost of the fact that I now don't know where my data point started in this direction there. So you lose a bit of information for the benefit of compression and for the benefit of tractability. And that's going to be a common theme we're going to get to in the next few weeks, right? Is this idea of how many dimensions do I need to keep to allow my algorithms to work efficiently? How much information can I tolerate losing while dropping rank considerably? Okay. Is everyone happy so far? You guys could follow that that calculation if asked to in a test. Cool. All right. So now we want to generalize this into arbitrary dimensions. So we want to generalize onto a one-dimensional subspace aligned to an arbitrary low-dimensional subspace U with the dimension of M greater than or equal to 1. So again, you always at least need to be projecting onto a line. Okay. So here's an illustration for a projection onto a two-dimensional subspace of R3. Okay, so we're now projecting onto the grayed out area from 3D space. Okay, it might look really nice in this figure as well that this grayed out area is like kind of lying quite flat. So it looks like we're completely ignoring that third dimension. But again, it can be embedded in R3. Okay, your vectors themselves can still have 3 values, but now we're only going to be representing it in terms of 2 basis vectors with 2 coordinates, lambda 1 and lambda 2. Okay? And then maybe just say for anyone trying to map this onto the ideas of changes of bases and things like that, I consider this a transformation. Okay, so I don't consider this a change of basis or try and square it with those concepts. I take it somewhat for granted as being a transformation. Reason being is because number one, I'm telling you what basis I'm projecting onto. So again, we're fitting with those ideas that transformations change, or I have to be told what I'm projecting onto with the transformation. But also, I'm losing information. So it's not a case of I am taking a vector and just re-representing it. I am actually changing the line, all right? I'm actually taking x, some value in space, and losing information. Okay, that's an example of a change of the line, so it's a transformation to me. All right, and that maybe, yeah, I like keeping consistent with those sorts of things as well. Okay, but the good news is that what we just did in 1D holds almost directly into high dimensions. You just need to be careful about the inner product that you're using. Okay, that is the one case where now it gets really murky if you want to be completely general. But it's all about consistency. So once again, we know that the fastest way to get onto our the plane that we're projecting onto U is to just directly project onto it, which will give us the orthogonal mapping, or the orthogonal projection down onto it. And so we know that we will be 90 degrees to the plane. In other words, and this is important, this red vector is 90 degrees to every basis vector that we're projecting onto. Not just one, every single one of them, okay? So let's assume that B1 to M is an ordered basis of U being a subspace of Rn. We know that for any x sitting in Rn, that there is a projection onto U, and this means that there are lambdas, multiple of them now, because we have multiple basis vectors, all right, in R, such that we can build our projected matrix, our projected vector out of those basis vectors, okay? So once again, we're now projecting onto M basis vectors, and so we will have M coordinates in that space, okay? Okay, and that same three-step procedure will be used again. So we start off by finding the coordinates of our line in our new basis. So find the coordinates lambda 1 to m of the projection such that the linear combination exists, and we can always write this linear combination out as b lambda. Okay, once again, this is us saying, well, b1, b2, b3, however many you want, times by lambda 1, lambda 2, lambda 3. These are vectors. But again, it always helps to maybe remember that it still works the same way as the dot product. So what we're ultimately going to do is lambda 1 times by b1, the vector, plus lambda 2, the coefficient, times by b2, the vector, and so on. Okay, that's a linear combination of vectors of the columns of your basis. Okay. And so that's now what we're trying to solve for, and ultimately, again, we're stacking our basis vectors into columns, and then the lambdas is just a single vector that represents our coordinates in terms of that space, that representation. Okay, so pi of u is going to be the closest point in U to X, to our original space. All right, U being, again, the gray area. Okay. This occurs when the projection minus x is orthogonal to u, and so this applies that pi of u of x to the projection onto the subspace minus x must be orthogonal to all basis vectors of u. I did mention that already. Okay, so to start off with, we're going to start by just saying, well, okay, it needs to be orthogonal to all my basis vectors. I'm just going to write it out as that literally. Okay. For this example in the slides, we still use the dot product, right? So we're going to be using the dot product, but it might be a good idea, or it's a nice idea, to try and think about how you would generalize this to arbitrary inner products, where we know that now what might happen here is you would have b1, x minus pi of u x. With an arbitrary inner product, you get b1a of then x minus pi u of x. Okay, you can be completely kind of completely general about this, and all that's happened now is I have that metric, what's called usually a metric tensor, but I have that metric, that matrix in the middle telling me how to measure distance properly. That's now sitting in the middle there. Okay, but again, I promise you, I'm going to ask this not with a metric. Okay, it gets very messy, it gets hard, so you'll get the Euclidean dot product in the test if this question comes up. Okay, so we've now started by writing out our constraints. My projection must be orthogonal to all of my basis vectors. So using equation 17, the system can be written slightly more compactly as follows. So all I'm going to do is now just group, write out the projection in terms of lambda. So I'm just going to use that representation there and substitute it in here for all of those terms. Okay, but for most of you, you'll recognize that also we can make this even easier for ourselves, and we can package our basis vectors into a matrix. Okay, and so if what we were usually doing with our basis vectors was saying b1 as a vector, b2 as a vector, B3 as a vector. But now we're dealing with those things transposed. We're now going to package them sideways. So it's B1 transposed row vector, B2 transposed row vector, B3 transposed row vector. Okay? And that's going to get packaged up in there. Okay? Does anyone want to just tell me why this would give us an m by n matrix? Where is the m coming from? Where is the n coming from? I don't have water today to make it awkward, so I'm just going to stare at you for 2 minutes. Yeah, what's up?
The m vectors, which is incomplete.
Okay, so you want to try say what it means about the subspace. It's embedded in Rn, so that's where the n comes from, right? So you're correct. What you said is correct. I just like the saying that it's the subspace is embedded in Rn. Again, it means that there's this plane sitting in n-dimensional space, but there's only obviously then m of those basis vectors. So you're correct. Okay, and so now we have a compact representation of this. This is just my original matrix B transposed. Okay, and then this stays the same over there. All right, and so when we FOIL out B transposed X, and we can FOIL it out again, B transposed B lambda, and we take over the B transposed X, so you just kind of sort out these negative signs. What we end up with is that B transposed B lambda must be equal to B transposed X. Okay. The equation 25 is called the normal equation if anybody really cares about that. But note that B transposed B is invertible because B1 through Bm are linearly independent. Okay? This is also a point that matters. Our basis vectors are linearly independent, but also the matrix we got out was the smaller of the two dimensions. That means that it's rank M. If we were doing it the other way and we got an n by n matrix out by doing the product of B transposed, okay, we would now have an n by n matrix, but it would be rank M, where M is less than n. In other words, that is now a singular matrix. All right, the rank is lower than the number of rows or columns we have in the square matrix. It can't be inverted. So that's very important. And if you get that wrong in a test, if you do it the wrong order, you won't be able to invert it, and it's going to make your life hell. Make sure that this projection that you get afterwards is the smaller of the two. That's how come you're keeping it at an invertible matrix. And we know that that's going to work because we have m linearly independent columns. And so we know that the matrix B has rank m. And so when we multiply B with itself, it keeps the rank the same. So it's rank m. Okay, and then when it's m by m, rank m is invertible. Okay, and so the good news means that now we can just invert this on both sides. So we're just going to go, B transposed B invertible on both sides, and we end up with that equation there. Okay, and that is the entire multiplication for lambda. Okay, lastly, then finding the projection is now just the same idea as before. So we have that once we've projected onto the subspace, we know that the new data point is written as a linear combination of our basis, the linear combination coming from our lambda coefficients, or our coordinates, multiplying by our basis B. Okay, and remember that in this case, you're always representing basis on the left, multiplied by our coordinates on the right. Okay, again, if you need to think it through, it's always just this representation here, B1, B2, B3, times by coordinates x1 or lambda 1 or whatever. Okay, and so in that case now we just have another B slapped onto the end of this equation here. Pretty easy. That is our new vector, which is after I've done this projection, I have both the coordinates and the basis, and so I can write it out together as that full linear combination, which is the real representation of my vector. Okay. Once again, you could have to change your basis, in which case you would then have, that basis vector times by, make sure I do this right, some kind of forward transform with the backwards transform, let's call that hat or whatever, times by lambda. You can do the forwards and backwards transform in the new space as well. You can keep it going, but again, I see this as a chain, as an actual mapping that we're doing, all right, to try and square it with all the other things that we've done. Okay, so now the last thing to say is, can we find what the projection matrix is? We don't want to go through this process every time we want to project onto the line. We just want to know what an equation is for a mapping from x to its updated value, right? From the original vector onto the new basis. And so that's just this bit off the side here. Okay, that's your orthogonal projection matrix. Okay, so again, in the test, I can ask you for any of those three steps. What's the coordinates? What's the new vector? What's the projection matrix? Okay, everyone happy so far? We're just waiting for this to be over. All right. I don't suppose anyone's online aside from me, so I won't ask that. Okay, so again, you can reiterate the previous points, which is to say that the projections we've been working with produces a vector in Rn. However, you no longer require n coordinates to represent that projection, but only as many as you had basis vectors, the dimension of my subspace. Okay, so that's m coordinates with respect to our basis vectors b. And again, the whole idea here is that if your projection space is much lower dimension, then you can save a lot of these coefficients. And these coefficients is usually how we're storing data. A lot of the times when we're storing data, it's kind of implicit that we're doing it with respect to a Euclidean basis first. Okay, so in which case the coefficients and the vector itself are the same thing, because my basis is just the identity. So whether or not I have b lambda or lambda, it's the same thing, right? And that's true of eigen decomposition as well. In singular value decomposition, we start with that assumption that our original basis is the identity. But it doesn't have to be that way. And it's important to remember that what we're usually doing is working with coordinates in terms of the basis. Okay. So if we're projecting onto an orthogonal basis for U, this can be simplified as follows. And this is one of the reasons why we like orthogonal bases, orthonormal bases. All right. So again, orthonormal basis. Each basis is orthogonal to all of the others, and it has its own norm is equal to 1. All right. The inner product of bi bj is equal to 0, and the inner product of bi is equal to 1. Okay, that's an orthonormal basis, and then we package it together, we get B, which is an orthogonal matrix, but we know that that also means that all the columns are normal. Okay, and so that's really nice, because when we try and solve for then the pi mapping, we end up just simplifying B transpose B. That's invertible, but we know that it's the identity matrix, and the inverse of the identity matrix is the identity matrix, and so we end up with B transposed. Okay. So it becomes a lot simpler to compute. In reality, you can avoid doing any inversions. Okay, and so this is much faster computation. Secondly, this has a really nice interpretation in terms of solving inhomogeneous systems of equations. So again, when it's inhomogeneous, we have some b on the right-hand side. If it's a homogeneous, then that's 0 on the right-hand side. Okay. So recall that if we're solving for ax is equal to b and it has no solutions, it means that b is not in the span of a. However, but we can try and find the x that is closest to b as in an approximate solution. And if you try and solve this, the idea here is that what you're going to do is multiply on the left-hand side by a transposed, right? And once again, we get back to that case where a may not have been full rank. Well, it couldn't have been if b was outside of the span of A, all right? So if B is outside of the span of A, it means we know A is not full rank, okay? But when we go A transpose A, what we're doing is we're now going an M by N times by an N by M, where M is the smaller dimension. And once again, if A had linearly independent columns, then we know that that's going to give us something that we can invert, okay? So I'm just going to group that together and say, well, why don't I invert that? And as a result, this will all fall away. And if we keep consistent with what's going on the right-hand side, we multiply by A transposed, and then we multiply by A transposed A inverse. And so we equal X is equal to that. And this is our equation at the bottom here, and this is known as the Moore-Penrose pseudo-inverse. It is a information losing system, right? You've just multiplied on the left-hand side by A transposed, where A transposed didn't have full rank. So you've lost information at that step of the process. But after that, after you've lost this information, you are now working in a full rank system that is invertible. And so now you can do the inversion and get to your closest possible approximation for X. And it just so happens that if you compare those two equations, if you compare this strategy that we just did of trying to get something that is invertible and then inverting that, it turns out that that's actually the same equation on the right-hand side here as the orthogonal projection mapping. All right, it's actually that. Okay. This is a really nice interpretation in terms of the fact that if you cannot solve your system of linear equations and you use the Moore-Penrose pseudo-inverse, you then get to the closest possible approximation. And that closest possible approximation is the one that is also orthogonal to your system. Okay? The closest you can be to satisfying this vector X, which is the thing you were trying to represent but didn't have rank to represent with, the closest thing you can get is just to sit right underneath it within the space you can represent. That's the interpretation. And it just so happens that that's also how you project orthogonally onto that space. You're solving the same thing there. Does that make sense? You guys doing all right in the back? You good? Yeah. The little thing at the bottom, right? Alrighty. Let's find a good checkpoint. That's a good checkpoint. Next week we'll continue with the Gram-Schmidt orthogonalization algorithm. It's a nice, I find it to be quite an intuitive algorithm to get an orthonormal basis. So again, if you start with a basis, we know that that is a representation of space. We know that those vectors are linearly independent, but we don't know that they're orthogonal. We don't know that those vectors are unit norm. And so Gram-Schmidt will give you one of those. And what's nice is that when you have an orthonormal or orthogonal matrix, we know that its transpose is the same as its inverse. And then that makes things much, much easier. So Gram and Schmidt came up with an algorithm to help us do that. And it just uses a whole bunch of orthogonal projections one after each other. Last thing I just want to mention then is at the top of the slide is let me scroll all the way to the top. There we go. Top of the slide is a OneNote that I've put together. If we have time next week, I'll go through it, and I will also maybe just try to clean that nonsense up at the bottom left. But this is also an interpretation that I like of what a dot product is doing. So if anyone is going to go through this in the next few days, I'll just chat through this for a second, but I'll go through it properly again next time. But I like to think that there is a difference between a column and a row vector. To me, the only vector in terms of a dot in space or some kind of arrow, let's try to make that bigger, some kind of arrow is a column vector. I like to think then of row vectors like this as ways of measuring space. Okay. In other words, when you have a vector like this, what you've done is you've come and you've put like this purple vector down there. And that purple vector is pointing in the direction of 1, 1. You can see it's not the best coordinates, but it's 1, 1. So it's pointing up to 1, 1, right? And that is because that's the vector I defined it as. But what it's really doing is creating these concentric lines in like you guys would know this if you did like geography, right? Like when you want to represent elevation along a cliff, you always write those little circles, and the closer the circles are to each other, the quicker your elevation. It's the exact same idea. This row vector is defining these lines here. Okay? And so if we then come along and halve the length of the vector, what you're ultimately doing is doubling the gap between these two things. And if you take the dot product of the same vector, so 7 and 3, with both vectors, right, with both of our row vectors that are measuring space, what you end up with in both times, if Devin's also drawn it correctly, is the number of these lines that this green vector intersects. Okay, so in terms of this space, there is 10, and if you go like count it out, you've intersected 10 lines in that direction. If you then double the space, you then get 5. So halve the vector, double the number of the size of the space, you then intersect 5 of these lines. Okay, and that's kind of why when something is orthogonal, when it's pointing out in this direction here, you're not intersecting any lines, right? Or you're intersecting this red one that, like, you know, sits over there or something like that. But that's the whole idea, is that like this, when you are doing a row times a column vector, you are counting how many of these lines my column vector intersects when I'm using the row vector as a measure of distance. Okay, we can go through it again next week, but in reality, this is kind of the whole example. And then that's what I went through last week, where I gave you the angle calculation, and then I just pulled in the norms using the bilinearity. And so the only thing that was left between your two vectors, A and B, that can be measured now that you've normalized their distance, is just the angle between them. And that's the whole idea of why that algorithm works, or that calculation works. But I will actually derive it next week down here for you guys, just so it's a little intuitive where that comes from, because I find that derivation at the bottom quite unintuitive. So we'll go through it. All right, any questions before we end off? I think if you did ask a question, your colleagues would beat you. So let's end it there, and I'll see you guys next week.
I had a question.
Oh, really? Risky business, man.
That word, the pseudo inverse.
Yeah.
You said it's information that only when dealing with matrices that are different sizes.
Correct.
Otherwise, it's what's up. Like if you have a 3 by 3 and a 3 by 3.
Yes. Correct. Correct. Cool. All right. Thanks, guys.